I think we can start. Welcome everyone to this week Autonomy Talks. This week is a pleasure to have with us Dr. Kenan Zhang, who is a postdoctoral researcher in the Automatic Control Lab here at ETH Zurich, working with Professor John Ligeros and Professor Andrea Krause. She actually will join EPFL as an assistant professor next year. And something about her, so she completed her studies, first the undergrad and then the master's at Tsinghua University and Carnegie Mellon University, both in civil engineering. She then moved to US, where she obtained her PhD in transportation engineering from Northwestern University. Her research focuses on mathematical modeling and optimization for urban transportation systems, and she's specifically interested into emerging mobility services and technologies and applications of game theory and machine learning in transportation. Today's talk will be about games and control on traffic networks. And since this touches many of the topics we are interested into in our group, but broadly in our audience of the Autonomy Talks, we are very happy to listen to your talk, Kenan. So go ahead, the stage is yours.
Okay, thank you for the introduction. So hi everyone. So first, thanks for having me here. As introduced by Jolie, my background is transportation, and my research has been focusing on the equilibrium analysis of a transportation system. So this talk will be very different from the other ones in the sense that I will talk more about modeling instead of theories and algorithms. So I summarized this talk with this title, Game and Control on Transportation Networks, but I put quote mark on the control here because, as you will soon know, it is not the optimal control on a dynamic system, but more discussed from a higher level planning point of view. So this is the outline of my talk today. I will first introduce a classic model in transportation research called traffic assignment. Then I will present two traffic management projects using this basic model, and both of them are inspired by autonomous vehicles. After that, I will switch the topic to on-demand mobility services and present a model for the ride-hail vehicle routing. Although it comes from a very different context, it turns out the routing behavior of ride-hail vehicles share many similarities with the classic traffic routing. Also, if you have questions, please just stop me and ask anytime during this presentation. So now let's start from the very basic traffic assignment problem. And actually this model is developed in the 1950s, but it's still widely used in the transportation research. So the problem originally comes from the four-step model for urban travel forecasting. So in the urban demand forecasting, we normally start by predicting the total travel demand and allocating them into different origin-destination pairs. Then we predict the travelers' mode choice based on their demographic characteristics and also the cost of available travel modes. For instance, the high-income people are more likely to choose driving, while low-income people are prone to public transit. So the last step is to assign these trips onto transportation networks. Normally, the last two steps go iteratively because the travel cost really depends on the trip assignment. And in brief, the traffic assignment problem aims to predict the traffic flow on each link given the network topology and the travel demand. And here is a very simple example. Suppose there were 10 people going from node A to D, and in this particular network, we have a 3 paths. And if the travel flow are distributed as 4 to 4, then the link flow pattern will look like this. Normally, we assume the travel time on each link is an increasing function of the link flow, then in this particular case, the link on the top left and lower right are more congested than the others. So this slide shows the main assumptions imposed on the basic traffic assignment model. So first, we assume the travel demand between each OD pair is known and deterministic. And second, the travel time on each link only depends on the traffic flow on this link. And the mapping is also known and deterministic. Since the number of travelers is very large, we assume they can be represented as continuous mass, and each traveler's impact on the aggregate behaviors is negligible. And next, we assume the routing of each traveler is also deterministic and follows a certain behavior rule. And finally, the traffic flows are loaded on the network at a single moment, so there's no evolution of the traffic dynamics. So you may feel these assumptions are very restrictive and unrealistic. When I first studied this model, I have the same feeling. So here I put the quote that is also in my course slide. All models are wrong, but some are useful. So through this talk, I hope I could somehow convince you that this model is indeed useful, even though it is highly simplified. So what are the applications of the traffic assignment model? The first one is, again, the urban travel forecasting. It helps us get a general idea about how the traffic will look like in a long time period ahead. Second, this model supports strategic planning. An example problem is whether building a new highway could cause more traffic congestion. So you may find it counterintuitive because we are actually adding new capacity to the network. But this problem indeed happened in real practice, and it is well known as the Brace paradox. And the third application is similar to the previous one. People have been using this model to evaluate different policies, such as different road pricing schemes. However, it should be emphasized that this model only produces general insights instead of accurate prediction. So that's also why this model is mostly used in the high-level planning problem. So now let's get into more detail about the model and define some useful notations. So we consider travelers between OD pair W can choose a path K from a path set based on the path travel time CK, and the path travel flow FK between the same OD pair sum up to the total travel demand between this OD pair. Also, the path flow can be transferred into the link flow, and we use this link path index matrix to do the transformation. And each entry in this matrix denotes whether the link is on a given path. And finally, we consider the travel time on a link is given by a link performance function, and the path travel time is the sum of link travel time. So the traffic assignment problem is formulated as a static routing game because travelers make routing decisions based on the traffic flow pattern, while the traffic pattern is an aggregate representation of all travelers' routing decisions. Since we also assume each traveler's impact on the aggregate traffic pattern is negligible, the outcome is represented by this wardrobe equilibrium. So if we use UK to denote the cost of path K and U star to be the minimum cost among all paths between the same OD pair, then at the equilibrium, no one can further reduce the cost by unilaterally changing the route choice. And mathematically, we have this complementary condition. So there are two important equilibrium concepts in the traffic assignment problem. One is user equilibrium, where all travelers aim to minimize their own travel time. And in this case, the path cost is set to be the path travel time. When the link performance function is monotonically increasing and continuously differentiable, the link flow pattern at the equilibrium is the same as the unique solution to this BI problem. And here, the X star is the equilibrium link flow, and the omega is the feasible set that contains all the information about the demand and the path. The other important concept is system optimal, where all travelers choose their route to minimize the total travel time. It turns out that this problem can also be formulated as a BI problem. And the only difference is that we replace the link travel time with this link marginal cost, which essentially measures how much each additional traveler contribute to the total travel time on this link. And in this case, we actually define the cost of each path as the sum of link marginal cost. So clearly the two states, the UE and SO states, lead to different total travel time as long as the link travel time is not a constant. And in other words, the network is actually more congested if travelers are self-interest. A common measure for this inefficiency is called a price of anarchy. And in our case, it is defined as the ratio of total travel cost between the UE state and SO state. When the link cost is linear, it is shown that this price of anarchy is bounded by 4/3. Well, if the link cost is polynomial, then this bound increases with the polynomial degree of the link cost function. So in the transportation literature, a great amount of effort has been devoted to addressing this inefficiency due to selfish routing. And the most straightforward idea is to charge this marginal toll, which is the difference between the link marginal cost and the link cost. But this is only theoretically appealing because in practice, it would be almost impossible to compute this marginal cost. And also, it used to be infeasible to charge a toll that constantly varying over time. So given this, given this difficulty, people have been discussing a more practical tools, such as the cordon-based toll, which has also been implemented in real practice. Another issue that has been discussed a lot is the fairness. So at the system optimum, travelers between the same OD pair may have different travel costs or even suffer from a higher cost compared to the UE state. So this also make it hard to justify the toll scheme. So people have been discussing the Pareto improving toll, which ensure that no traveler is worse off compared to the UE state. And finally, there's another interesting direction called the tradable credit. It can be seen as a type of virtual currency that is paid to or buy from the authority to get access to road facility. So it is also proof capable of pushing the equilibrium to the system optimal in theory. So all the traffic management strategy mentioned above aim to internalize the extra congestion cost into each traveler's utility. In other words, the travelers under this management schemes are still trying to minimize their own costs, except now the total cost is the travel time plus another price. But in the follows, I will discuss a more direct approach to congestion mitigation, which is through route control. So intuitively, we could simply recommend travelers to take paths that induce less congestion, but then the compliance would be the major issue. Why would people be willing to sacrifice for the social good? Fortunately, this directed route control idea is more likely to happen when we have autonomous vehicles. And this gives the idea of our first study, which is called an optimal ratio control scheme. In brief, we hope to control a fraction of autonomous vehicle in the network based on their OD pairs and route them to minimize the total travel time. And there are two conflicting objectives here. On the one hand, we hope to maximize the total travel time saving, while on the other hand, we also want to minimize the control intensity. So this problem ends up being a Stackelberg game. On the upper level, the leader decides which OD pairs and how many vehicles between them should be controlled. And the decision variable is a vector of controlled demand flow, which is represented by this tilde Q. The leader's objective consists of two parts. Remember, we have two objectives. The first part is this L1 norm of tilde Q, which measures the control intensity and sparsity. And the second part of the objective is simply the total travel time. And the gamma here is the trade-off parameter. Then the follower is a population of vehicles that are divided into two groups. Here, the UE users are human-driven vehicles and those autonomous vehicles that are not controlled. And their objective is to minimize their own travel time. And we use XUE to denote their link flow pattern. The SO users are the controlled autonomous vehicles, and they are routed to minimize the total travel time. And we use the vector XSO to denote their link flow pattern. So if this link performance function is a polynomial function of the total link flow, then we show that for each feasible control demand pattern, there always exists a solution to this lower level mixed equilibrium problem. And the total link flow pattern is unique. And with the same assumption, the existence of a solution to this ORCS problem is also guaranteed. So to solve this problem, we developed an iterative algorithm based on the idea of sensitivity analysis. Specifically, we start from the UE state, and in each iteration, we solve an additional demand shift delta tilde Q, given the current solution. And the second term in this objective function is approximated by the linear extension. And we showed that this gradient term can be approximated by the difference in past marginal cost between the UE and SO users. And the resulting upper level problem is then solved by ADMM. Then at the lower level, we update the demand shift and solve this mixed traffic equilibrium using Frank-Wolf algorithm with a joint line search step. So we test this model on two benchmark network, but the main findings are similar. So here I just include the results from the experiment on the SUFO network, which is a small network with 24 nodes. For benchmark, we also test this uniform ratio control scheme, which simply controls a uniform ratio of vehicles between each OD pair and route them as SO users. So the main findings from our experiment is that ORCS could reach a closed SO state by controlling a very small fraction of autonomous vehicles. In this left figure, we plot the total travel time versus the maximum control level, which is the maximum fraction of vehicles that can be controlled in the network. And we can also interpret it as the penetration rate of autonomous vehicles. So the total travel time of UE and SO are also plotted here for reference. And the right figure here plots the fraction of controlled vehicle versus the maximum controlled level. So as you can see, the ORCS achieves a similar performance as the URCS, but with a much lower control intensity. When the vehicles, when the 90% of vehicles in the network are controllable, we can approach a close SO state with only 10% vehicles being controlled. And the second main finding is that under ORCS, most OD pairs are either not controlled or fully controlled. So this figure plots the histogram of a control level, and the left bar shows the number of OD pairs that are not affected, while the right bar shows the number of OD pairs that are fully controlled. So as you can see, there are very few partially controlled OD pairs in the middle. So in fact, the main idea of congestion mitigation through route control is to detour some travelers from the most congested links. And in the first project, this is done by routing some travelers as the SO users. But in the second project, we aim to further reduce the intervention on the network. So in this so-called multi-hub control scheme, all travelers can freely choose their route, but some of them are asked to visit intermediate stops before reaching their final destinations. So from a modeling perspective, this is equivalent to doing a demand segmentation. So for example, we have if we have a one OD pair AB and we consider a single intermediate stop C, then the segmented demand pattern will have three OD pairs, AB, AC, and CB. And by flow conservation, the new demand flows between AB and AC must sum up to be the original demand flow, and those between AC and CB must be equal. And again, the MHCS is formulated as a Stackelberg game where the leader decides on the demand segmentation matrix lambda given a set of intermediate stops. And the lower level is simply a classic traffic assignment problem because all travelers can simply choose route to minimize their own travel time. And the problem also guarantees a solution if the link performance function is monotonically increasing and continuously differentiable. So the solution method is also similar to the previous one. At the upper level, we first linearize the objective function and approximate this gradient term, the gradient of the total travel time with respect to the segmented demand pattern using a method proposed in a previous study. And the resulting problem is then solved by some building algorithm in MATLAB. The lower level is simply the classic traffic assignment, so it can be easily solved by some conventional method. So this proposed control scheme is also tested on Zürich network, and here I list the 3 of the measures we use to evaluate the system performance. So the first one is the relative travel time saving, which essentially measures how close the final state is relative to the system optimal. The second one is the total unfairness, which is computed as the total difference between the travel time of a selected path and the shortest path. So it measures how much the controlled travelers sacrifice for the system. And the third measure is saving to unfairness, which is computed as the total travel time saving divided by the total unfairness. So clearly this control scheme is reasonable only when this value is greater than 1. So this table shows the main result in our experiment, and there's in 3 scenarios where when there's only 1 intermediate stop, 3 intermediate stops, and also the SO state as a benchmark. So the main insights are very similar to ORCS. We can achieve a majority of the potential travel time saving with a fairly mild intervention on the network. In this single stop scenario, only 6% of the vehicles are controlled. And besides, we found there's no significant difference between the 1 stop case and 3 stop case in terms of the saving to unfairness criteria. So a brief summary of these 2 projects. So first, we know that the selfish routing is not efficient and induces additional traffic congestion. To deal with that, we may design a pricing mechanism to internalize the congestion cost into each traveler's utility, or we can directly control the route of some travelers. Thanks to the fast development of autonomous driving, the latter will become more possible in the near future. And our study showed that a well-designed route control scheme can correct most of the inefficiency with very few interventions. In terms of a future work, one critical issue that has not been addressed is the unfairness. Clearly, if there exists a significant difference in travel time between the controlled vehicles and non-controlled vehicles, no one would be willing to participate in our control program. One possible solution is to constrain the control scheme so that no one suffers from a larger cost compared to the UE state. So this idea is very similar to the Pareto improving pricing scheme. Another unsolved problem in the second project is the selection of intermediate stops. Currently, these stops are chosen by some heuristics, but this is clearly not optimal. And including this node selection will make the problem more challenging to solve. So we need to develop a new method. And also when the number of intermediate stops increases, the dimension of the decision variable will also increase fast. So we also need a more scalable algorithm. And thirdly, we only demonstrate the potential of this 2 route control scheme in a static model. So there's still a long way to go before they could be finally implemented in real practice. So our next step is to model the route control problem in a dynamic traffic scenario. So far, we have discussed the routing of general vehicles in a static traffic network. And in the rest of this talk, I will turn our focus on to the on-demand mobility services and discuss the routing of ride-hail vehicles. So the main question in this problem is how the ride-hail vehicles move across different regions in the city to search for passengers. And specifically, we would like to explain the vehicle distribution in a spatial temporal market and also understand how the different passenger vehicle matching mechanism would affect this distribution. And besides, we are also interested in the loss of efficiency due to the selfish decision-making of drivers. So why modeling the driver's behaviors is important for us? So for both the service operator and the policymaker, the driver's routing basically forms the basis of any optimization problem. In other words, we can design, operate, and regulate the service only when we have a clear understanding of how the drivers would behave. So before jumping to the model, I'd like to briefly review how this problem is tackled in the literature. So in general, the previous studies can be classified into two groups. The first one tackles the routing of individual drivers. So these studies either learn the passenger search strategies from data or design the optimal search strategies for individual drivers. And a common assumption here is that the market condition doesn't change when the driver updates his strategy. And this clearly doesn't hold when we consider the routing of a large fleet of drivers. So the second group deal with this routing of a fleet of drivers. These models can be divided into centralized and decentralized. The centralized model assumes all vehicles are controlled by a central agent. In contrast, the centralized model assumes drivers can freely choose their search locations to maximize their own utility. And these studies can further be divided to model-based and model-free. And in the latter case, in the model-free cases, drivers directly learn search policy through like a multi-agent reinforcement learning. Well, the model presented here falls in the model-based decentralized routing. So we first specify some system dynamics. We consider a spatial market that consists of end zones and discretize the time horizon into t intervals with identical length, delta. We also assume the trip durations are multiples of delta. And next, we use QIT to denote the demand rate from zone I during time t, and use the alpha ij to denote the demand fraction from I to j. And on the supply side, there is a fleet of m homogeneous drivers traveling across zones to search and deliver passengers. So at the beginning of each time period, each idle driver can choose to either stay in the current zone or move to a neighbor zone for passenger search. The collective behaviors lead to the relocation flow xij, and the total number of vacant vehicles after relocation is denoted by yj, which is simply the sum over xij. And next, we assume the passengers arriving in J can only be matched with vehicles in the same zone, and the matching process leads to a meeting probability MJ, which is the probability of picking up a passenger in J by the end of period T. Finally, The matched vehicles in J will join with the vehicles that drop off passengers by the end of time T, and together make a new search decision in the following time period. So we model each driver's routing behavior as a Markov decision process. First, there were two types of states. The vacant state is indexed by the current location, while the occupied state is indexed by the origin, the trip origin, destination, and elapsed travel time. Similarly, there were two types of actions. When the vehicle is vacant, the action is the next search zone. When it's occupied, the vehicle can only continue its current trip. So we just use a dummy action here. As for the state transitions, those from a vacant state are stochastic and depends on the meeting probability and trip destination. As for the transitions from an occupied state, they are simply deterministic. We consider drivers receive an immediate reward upon each pickup, and the reward associated with other transitions are simply zero. And finally, gamma is the discount factor. So since the transitions from occupied state are deterministic, we can simplify the value function as the expected return from each vacant state. And in this formula, the pi it denotes the probability of relocating from I to J. If the drivers pick up a passenger, then the return would be the immediate reward plus the discounted value from the next vacant state. If the driver fails to find a passenger, then the return is the discounted value from the next time step. So the objective of each driver is to find a best search strategy that maximizes the expected value from the initial state. And this can be easily solved through backward propagation given the meeting probabilities. However, as the meeting probability is a function of a vehicle supply, and the vehicle supply represent the routing strategies of all travelers, the problem turns out to be a routing game. So we model the collective vehicle routing as an MDP routing game, and here we also assume the fleet size is large enough so that each driver's impact on the aggregate behaviors is negligible. To describe the equilibrium state, we define the Q value associated with an aggregate strategy pi, and accordingly, the wardrobe equilibrium is defined on an aggregate strategy such that no one can achieve a higher Q value at any state. We further show that this wardrobe equilibrium is equivalent to a fixed point. And specifically, given the vehicle flow pattern, we can solve the optimal strategy. And in turn, we can load the vehicle flow pattern based on an aggregate strategy. And the existence of the equilibrium and the solution algorithm are both established based on this fixed point property. So we further extend the problem to consider corroborative routing, where drivers choose search locations to maximize the total return. We show that the optimal search strategy in this case can be derived as the wardrobe equilibrium with a different reward function. And the new reward here is proportional but less than the original one, because the partial derivative here is normally negative. It also indicates that the selfish routing of drivers is not efficient and cause extra congestion in the matching process. similar to the classic traffic routing. And to correct this inefficiency, we need to add this additional term that penalize the vehicle aggregation in each zone. And this is also similar to the congestion toll. And another important insight from this result is that we could do vehicle coordination in a decentralized way. If these vehicles are human-driven vehicles, this can be done by properly pricing each trip. If autonomous vehicles are operated, then this turns out to be a particular reward design. So next, I'd like to spend some time explaining how we derive the meeting probability. We assume the waiting passengers are uniformly distributed in the space, and each driver can search an area A during each time period. Then the meeting probability is derived as the probability that at least one passenger appears inside the driver's search area. We then specify the general model for two particular service modes. In street hail, passengers hail vehicles on the street as they pass by, while in e-hail, passengers and vehicles are matched in real time by a central platform like Uber and Lyft. So to derive the passenger density pi, we first write it as the multiple of arrival rate Q and waiting time W. Then we replace the waiting time W with the formula derived in our previous work, which are based on a physical matching model. Since the street hail vehicles can only cruise along street, the search area is computed as the search distance over the road density. As for the e-hail, we assume the zone is evenly split to each vehicle. So it's the zone area divided by the number of vehicles here. And there's a special case in e-hail when the market is oversupplied, there's at most one passenger waiting at each moment. So in this case, the general model doesn't help, but the meeting probability is easy to derive. So this slide presents the meeting probability formulas. And in all scenarios, we can show that the meeting probability is given by a function of this demand-supply ratio. We further calibrate these formulas with agent-based simulations. And in these two figures, the data points are generated by the simulations while the lines are drawn from using the model. As you can see, the meeting probability of e-hail grows much faster than street hail with the demand-supply ratio. This is mainly because it has a more advanced matching mechanism. And if we zoom into the low demand region, we can see that the street hail model still perform reasonably well, but the normal e-hail model tends to underestimate the meeting probability. And in this case, the adjusted model produces a better estimate. So we first test this routing model on a 4-node network where every 2 nodes are neighbors except nodes 2 and 4. And the figures here plot the performance of our current solution algorithm. And here we define the gap as the total absolute difference between the Q value with the positive relocation flows and the maximum Q value. And this value is normalized by the total maximum Q value. And as shown in this figure, the convergence rate is sublinear, but in the cooperative routing, the objective function can quickly converge. And compared to other scenarios, the cooperative routing under e-hail ends up with a larger gap after the same number of iterations. Our second numerical experiment is constructed based on the city of Chicago. In the network, each zone is represented by a community in the city, and the time horizon is discretized into 64 quarter-hour intervals. We then use the public TNC and traffic data to estimate all the input variables, such as the demand pattern, the trip fare, trip durations, and traffic speed. We test two fleet sizes. One has 3,300 vehicles, and it denotes a slightly undersupplied market, while the 9,000 vehicles fleet leads to a oversupplied market. We use these four measures to evaluate the system performance. And here the price of anarchy is defined as the ratio of total return between the cooperative scenario and non-cooperative scenario. And this incentive multiplier here is derived from the cooperative reward function. So this slide reports the total return and price of anarchy in the four tested scenarios with different modes and the fleet size. As expected, in all cases, we found the e-hel always achieve a higher total return, but it also leads to a higher inefficiency, especially when the market is oversupplied. In contrast, the efficiency in e-hel actually reduces as the fleet size increases. This slide presents the temporal vehicle utilization rate. For reference, we also plot the temporal demand pattern here as the gray dashed line. Also here, the green lines are drawn to compare the two modes. So as shown in this top plot, the vehicle utilization rate is similar between the two modes during the demand peak. However, in the middle of the day, the e-hel achieves a much higher performance, also thanks to the more efficient matching when the demand is relatively low. And it also explains the higher total return of e-hel showing the previous slide. And with a larger fleet size, the gap between street hel and e-hel actually reduces, mainly because the market is oversupplied. And here we found that these extra e-hel vehicles also couldn't find the passengers. So that leads to a lower, a drop in the utilization rate. And finally, this slide shows the incentive multipliers over time. And recall that these multipliers are zone-based, so we plot the median value as the black lines, and also the maximum and minimum values as the blue and orange bars here. And the first observation is that these multipliers have a similar trend over different zones, and they are the highest during the demand peak and lowest in the middle of the day. An interesting case is the street hel with the smaller fleet size, where we found that the multiplier actually dropped below zero, meaning that drivers operating during this period are actually penalized. And another interesting finding is that when we have a really large fleet size, these multipliers are mostly zero, meaning drivers do not receive immediate reward at all. And it also implies that when the market is oversupplied, the best strategy is to simply randomly search across all locations. So a summary of the second part, we show that the ride-hail vehicles are also playing a routing game and there exists the congestion induced by the matching process. Similar to the classic traffic routing, the efficiency in this ride-hail vehicle routing can also be corrected through a certain pricing mechanism. And for future work, we first plan to extend the vehicle state to first account for the flexible working schedule in the ride sourcing services like Uber and Lyft. Therefore, these drivers could temporarily leave the market when there's not sufficient demand. We are also planning to integrate this model with the electric vehicles so that by adding additional charging state, we can study both the charging behaviors and the routing behaviors. And so far, we have assumed the passenger demand is fixed, but in real practice, passengers are sensitive to the waiting time, which is also a function of vehicle supply in each zone. So to complete this spatial market equilibrium, we need to include the demand model and also connect it to the vehicle routing. And the third task is to improve our current solution algorithm, and we hope it to be scalable and semi-distributed, which align with the real operations of ride-hail services. And lastly, although we show the optimal incentives can help push the equilibrium to system optimal, it is still unclear how we could implement it. Especially, we observe this result that the incentives could be negative sometimes. So also another issue is in practice, it's really hard to obtain perfect information about the meeting probability function. So we need to develop certain learning algorithm to determine the optimal incentives based on the observations of aggregate measures of the market. So with that, I will end this presentation. Thank you very much for listening, and please be free to reach out if you find potential collaboration opportunity. Thank you so much.
Thank you, Kenan, for the great talk. I open now the stage for questions. If you have questions, you can simply unmute yourself and ask. Maybe I'll start with one, since audience is a bit shy today. I actually had a question regarding the first part of the talk. So I think mostly regarding slide 11. And my question was a bit related to the next steps you mentioned. I was a bit curious. So you said you were looking for static, you were looking at the static case and you wanted to extend it to the temporal case.
Yes.
And I wanted to ask you, what are the challenges there, or what are the steps there you would like to pursue?
Yeah, I think the main challenge here is to first model the traffic dynamics. So we do have a different version of dynamic traffic assignment model, but the key problem is that normally they are highly computational expensive. Whenever you want to do a network loading, it often either you use some aggregate traffic flow model or you use simulation, but both of them requires a lot of computation time. So in that case, if we do a bi-level optimization like this one, we actually need to solve the equilibrium given one control scheme and update that control scheme given the observed equilibrium. So if each equilibrium consumes a lot of time to solve, it's really hard to first run one iteration in the main loop, and also the second difficulty is how to derive the partial derivative. That is how what would be the response of the lower level equilibrium with respect to a small interpretation of your control scheme. I think these are the two challenges when you move from the static model to a dynamic model.
Okay, makes sense. Thank you. Any question from the audience?
I have a question. Hi, Kenan.
Yes.
Go ahead.
My question is about the last part, this pricing or this incentive mechanism. Can you just reiterate how that is computed?
The pricing, you mean the incentives, right?
Yes. So the extra term that you add to the cooperative reward?
Yes. Let me go back to. So this one. So basically, this term is derived from the equivalence between the basically the system optimal problem and the regional wardrobe equilibrium. So it's similar to the classic routing problem where you have the system optimal problem formulated as a optimization problem, and then you find the KKT condition of that, and you transform it into a classic traffic routing problem with a different cost function. So in this case, that's the similar. So we can show that from the system optimal problem, you can find so the proof is not find the KKT condition, but to show that the two formulations are equivalent.
Okay. And then I guess that would be converted to pricing somehow to actually implement it.
Yes, so the key issue is you need to solve this derivative. So basically, you need to know how the matching probability change with respect to a single with additional vehicles in the zone, which is not very easy to solve in real practice. And also, once you have this incentive, because this is normally smaller than one, this term is smaller than one, and it can be either further goes below zero, or for the drivers, they are actually penalizing when surging in certain zone. So the following question is how you distribute the revenue.
Okay, and my last question is that, okay, so this gets introduced on the immediate reward?
Yes, so the immediate reward is replaced by this term.
Okay, and then, but still, this leads to the system optimum at the dynamic equilibrium.
Yes.
Okay.
Yeah, so the key idea here is to show that if you use this reward function, the system will end up to the system optimal.
Thank you.
Thanks.
That's it for the question. Maybe I have also another one, which is in the final part of your talk, you showed this nice approach to do matching of vehicles with demand that somehow does more steps, more of the classic steps, because usually you have assignment, but also you have rebalancing strategies. Have you looked at how your solutions compare to standard rebalancing strategies, for instance, for vehicles? when they need to go and look for new demands in other locations?
So basically, this model includes the rebalancing things. So rebalancing means assume that the drivers just stay at their current location, then they never move to other locations, which is not optimal. So then we need to do certain rebalancing to match the demand and supply in each zone. But in our case, because we assume drivers are strategic, they are rational, they know full information about the demand pattern, so their behavior in some extent, in some sense, their behavior should be the same as the optimal rebalancing, along with the optimal rebalancing strategy. And in terms of specific rebalancing projects, I think it really depends whether the two results are the same. Really depends on how people model the market. I believe a lot of rebalancing strategies are derived based on queuing network, where travelers, like passengers and drivers, are meet at a station. So in our model, we hope to remove those stations and replace that with a spatial matching model. So I think that would make a different, leads to different result between our model and the rebalancing model.
Thank you.
Thanks.
Any final question? In case people realize they had questions later tonight, I think you left your email on the last slide, right?
Yes.
For people to reach out. Thank you very much, Kenan, for the great talk, and wish you good luck for the next adventures here at ETH and later at EPFL.
Thank you.
And thank you all for participating, and see you all next week for the next Autonomy Talk.